We've mentioned the Mach trim system a couple of times during this lesson. This will be explained now. Mach number is the relationship between the true airspeed of an aircraft and speed of sound. If the Mach number exceeds 1, the aircraft becomes supersonic. The 737 NGX has a maximum cruising speed of Mach 0.780. The Mach trim system provides speed stability at Mach numbers above 0.615. Elevators are adjusted relative to stabilizer position as speed increases, subsequently changing the control column neutral position through the elevator feel and centering unit. The Mach information is obtained from the Air Data Inertial Reference Unit, or ADIRU. Another similar system in the 737 NGX is the speed trim system. Like the Mach trim system, the speed trim system also provides speed stability. However, it's designed to return the aircraft to a trimmed speed by trimming the stabilizer opposite to the direction of speed change. This also increases control column forces. Some conditions that have to be met for speed trim operation are low gross weight, aft center of gravity, N1 greater than 60% or high power settings, airspeed between 100 indicated knots and Mach 0.50, and autopilot disengaged. Essentially, when the speed trim system comes alive, it requires the pilot to provide a significant amount of pull force to reduce airspeed and significant amount of push force to increase airspeed. You can see that there are quite a few ways that the elevator controls translate to direct and comfortable pilot control. Although quite complex, this elevator system is relatively simple compared to other aircraft flight control systems. Ailerons are movable surfaces on both wing outboard trailing edges that control the flight attitude of the aircraft about the longitudinal axis, more commonly known as roll. The ailerons are coupled so that when one of them moves down, the other moves up. There are 3 ways of achieving roll control on the 737 NG. Manually, by moving either control wheel, automatically, by autopilot input to move control wheels with actuators, or through flight spoilers. These will be discussed at a further stage during this lesson. During manual operation, the flight crew controls the roll attitude with control wheels that are interlinked mechanically in order to provide system redundancy. Just like with the elevators, the ailerons are actuated through pairs of cables that transmit force. Ailerons are also operated via the Aileron Power Control Unit, or PCU, that acts as an interface between the pilot's mechanical inputs and a series of hydraulic actuators that move the ailerons with wing cables. The aileron PCUs ensure that the ailerons are movable under any condition. Under normal operation, each hydraulic system controls a single aileron. In case of a hydraulic system failure, the working system may control both ailerons. In case of a total hydraulic failure, ailerons are still controllable mechanically. This condition is known as manual reversion. The upper PCU gets hydraulic system B pressure, and the lower PCU gets hydraulic system A pressure. The PCUs also limit aileron travel to 20 degrees up and 15 degrees down. When pilots turn the control wheels, mechanical stops in the aileron control wheel components keep the control wheel movement limited to 107.5 degrees left or right. The aileron feel and centering move the ailerons to a neutral position when there is no input. When the control column moves, a roller is moved, causing springs to extend and provide a feel force. When the control column is released, the roller moves to a detent, and thus the system moves to a neutral position. The captain's control wheel directly transmits force input to the aileron feel and centering unit, whereas the first officer's control wheel directly transmits force to the spoiler mixer. The spoiler mixer is further discussed in the secondary flight controls lesson. In case there's a failure or jam in either control wheel, the aileron transfer mechanism allows for both control wheels to be able to make roll commands. For example, if the spoiler system is jammed, aileron roll control may be achieved through the captain's control wheel. However, the first officer's control wheel and the flight spoilers would then be unusable. On the other hand, if one control wheel cannot move, the mechanism allows the other pilot to operate the other control wheel satisfactorily. The ailerons also have a trim system that works similarly to the elevator trim system, except that there is no trim wheel. Instead, 2 aileron trim switches are located in the aft electronic panel, and the aileron trim indicator is located on the top of the aileron control wheel. The indication is in units of trim, where each unit is equal to 6 degrees of control wheel rotation. The maximum trim available is 9.5 units, or 57 degrees, of control wheel rotation. When the aileron trim is in operation, an actuator moves the same aileron roller that we discussed before, causing springs to extend. This gives input to the power control units to move the ailerons, and the control wheels are also moved. Both aileron trim switches must be operated at the same time to supply power to the trim actuator. We saw before that the elevators and their systems were virtually in a straight line from the control columns in the cockpit. This is not the case with ailerons, where many of the components are located away from the airplane's fuselage. The very ailerons are located on the outboard trailing edges of both wings. This requires complex component linkages, which are achieved in the following way. The systems that run along the center line are connected to aileron body quadrants near the forward bulkhead of the main landing gear wheel well. Both body quadrants are connected to each aileron PCU. If one hydraulic system is off, the other PCU commands both quadrants. The body quadrants are connected to the wing quadrants through the wing cables. So when a wing cable moves, it moves the related wing quadrant and finally the respective aileron. Similarly to the elevators, there's an aileron tab that moves in a direction opposite to aileron movement to maintain positive balance. For example, when the control wheel is moved to the left aileron rises and the left aileron tab comes down. In the opposite wing, the right aileron comes down and the right aileron tab rises. This induces a noticeably higher angle of attack in the right wing when compared to the left wing, thus causing the right wing to go up and roll the aircraft towards the left. The ailerons also have balance panels and weights in order to decrease the force necessary to move them during flight. Flight spoilers are used to achieve significantly higher rolling moments around the airplane's longitudinal axis. These are a series of panels on the upper surface of each wing that rise when extended, thus creating an enormous amount of drag. Flight spoilers are only meant to be an aid to roll control, not the primary roll control method. There are 12 spoilers on each wing, numbered 1 to 12 from left to right. The most outboard and the most inboard spoilers on each wing are ground spoilers. Only the 4 flight spoilers on each wing provide roll control. During roll, when the control wheel turns left, the flight spoilers on the left wing move up, and in the right wing, they stay fared down. Flight spoiler panels on the 737NG have numerous functions, such as aiding ailerons in achieving roll control, aileron trim, speed brake operation during flight, and speed brake operation on ground during landing. Similarly to ailerons, the flight crew uses the control wheels to control roll with spoilers. The control wheels give mechanical input to the aileron power control units, PCUs, through the aileron feel and centering unit. From here, the PCUs supply mechanical input to the flight spoiler actuators that use hydraulic power to move the flight spoilers. The control wheels must be displaced more than 10 degrees left or right to actuate the respective set of flight spoilers. System redundancy is provided in the following manner. Each hydraulic system powers a specific set of flight spoilers in such a way that there's no asymmetrical deployment when there is a hydraulic system failure. One-sided deployment of spoilers is also avoided with this redundancy. Although most of the aileron operation seems difficult to understand and may need several reviews before it sinks in, keep in mind that most of what you've learned here will be transparent to you as the pilot flying. Having an understanding of the background workings of these systems may give you a greater appreciation for what goes on behind the scenes and what happens when things go awry. The rudder is a movable surface attached to the rear spar of the vertical stabilizer that provides yaw control of the aircraft around its vertical axis. The rudder may be operated by any of three ways: manually with the rudder pedals, manually with the rudder trim, or through the yaw damper. The yaw damper will be discussed in the following section. During manual operation, the pilot presses the pedals to achieve movement in the respective direction. For example, when the right rudder pedal is pressed, the rudder moves to the right of its neutral position, thus creating a rightward turning moment and achieving yaw to the right. The same logic applies when the left rudder pedals are pressed. Similarly to the rest of the flight control surfaces we've covered, rudder pedal movement inputs are linked to control valves in the rudder power control unit, PCU, via cables and linkages that also pass through the rudder feel and centering unit. In the case of rudder control, the pilot inputs are also linked to a standby rudder PCU that provides backup and system redundancy in the event of main rudder PCU malfunctions. There's no manual reversion available for rudder control, which means that if theoretically both normal hydraulic systems and the standby hydraulic system were to fail, rudder control would not be achievable. The probability of this happening is negligible. We mentioned earlier that elevators and ailerons had a pair of PCUs to control them. During normal operation, only one main PCU powers the rudder. The original 737 was designed using one dual valve with input from both hydraulic systems. This was partly responsible for a series of accidents associated to 737 rudder problems. In 2003, the Rudder System Enhancement Program, RSEP, was introduced, where the original dual valve that received input from both hydraulic systems A and B was replaced by one set of components and actuators for hydraulic system A, and an independent set of components and actuators for hydraulic system B. In this lesson, we'll discuss the rudder system schematic with RSEP installed.